All right. Okay, so welcome everyone. You might notice that Ariana is not here, our usual host. But Sam Tumalo and I are colleagues of Ariana's, and she's asked us to do the facilitation for this meeting because she's at a conference in Denver talking about this program and other programs that we work on with neurodivergent young people. So that's us. That's me and Sam.
Hi.
So I'm going to start, and Sam's going to do the end part where the survey questions for the evaluation. All right. So we're going to start with an icebreaker. Um, that's the first thing on the agenda. The next meeting is to be determined, so we will share that information with you. Um, Today's topic is very exciting. Whoops. It's going to be about the Mars mission and getting samples and preparing to be able to get samples back from Mars. So that's super exciting. Um, and then we'll do the feedback survey and then we will say goodbye. So we're just doing a quick icebreaker today, which is which bird are you today? So please, I don't know why I keep moving to the next slide. Um, Let us know in the chat how you're feeling. Which bird are you? Maybe we'll do in a 10-second timer and everyone will do like one of those waterfalls and everybody can let us know within 10 seconds. I'm going to
But
set a
just
share.
replied already.
Oh, everyone's replied already. Sorry, I can't see the chat because I have the thing for. All right. So, Sam, let me know who's feeling like this guy, number B.
B, we have nobody. Oh no,
Nobody
Maxwell.
feeling
Maxwell.
okay.
Maxwell.
Well,
Yeah.
that's good. Glad Maxwell's feeling
Yeah.
chipper like B.
Would like some of that energy.
Anybody feeling like C? I think I'm feeling like C today.
Maria and Sarah and Nate and Keith.
All right. Yeah, I had some ups and downs today. So actually, I should probably say A because that seems like ups and downs.
I said A too for the same reason.
I had a really good beginning and then things just sort of went downhill from there. All right. So let's move on. And we have a special treat because Jeff, the guest speaker, is going to talk for uh, an extra long time because it's super interesting. But we just wanted to go over the ground rules. So please remember, do not interrupt our speaker. If you have a question, enter it into the chat or hold till the end and ask aloud using the raise hand function, okay? And then please stick around for the end when Sam will be asking you some of the questions, the survey questions, to get your responses. All right. So I'm going to stop my sharing right now and let. Oh, actually, I'm not going to stop because I'm going to let Lynn, if you can't, let us know. Did Lynn? I feel like Lynn dropped out for a sec. Is that right? Let me see. Because I think Lynn's having internet problems.
Yeah, I don't see her.
Okay, so I'm going to introduce Jeff. All right. The guest speaker is Dr. Jeff Osterhout. Is that how you pronounce it? Hout?
You were close. It's Osterhout.
Osterhout. Okay. Um, Part of NASA's SMD Community of Practice for Education, which is called SCOPE. Um, and
Oh, good. Maybe I should
oh,
start
good. We
with
started
your
doing the
name.
introduction.
I
So
had
Lynn, Do you want to do more of the
I
introduction?
tried to,
This is all the stuff you know.
yeah, I tried to connect like twice with my regular internet, and it wouldn't connect. So then I went and got my hotspot, and I had to wait for my hotspot to power up, and I had to reconnect through the hotspot, but like it finally worked, sort of. Anyway, I am very pleased today to introduce you to somebody that we met through the SCOPE program. SCOPE is part of the Science Activation Program that their mission is to try to help other SciAct programs find NASA subject matter experts to interact with their projects. And so I request for speak for me to, and Dr. Osterhout was recommended. So he is at Tech now, and he, I guess, got a seed grant from Scope. If you switch to back to the next slide, or whatever that other slide was that had the rest of the stuff on it. Where's the other slide?
This one.
Yeah, there we go.
Yeah.
So he has a Bachelor of Science, right? Master's in Geology and a PhD in Geochemistry from UCLA, and he was postdoc at JPL. And so he worked scope to tell people all about Mars 2020 and hopefully the sample return mission if we manage to keep it in the budget. So he may he'll even say a few words about that part, but maybe he doesn't want to get involved. Anyway, I'm pleased to learn more about these things because I think we're going to be headed for Mars. So welcome, Dr. Osterhout.
All right. I'm going to stop
Thank you,
sharing
Lynn.
and then Jeff is going to share his screen. And then I can
Okay.
track the chat as well.
Yeah, thanks for the nice introduction. It's really great to be here. I really appreciate the invitation and excited to talk a little bit about the Mars 2020 rover mission and preparing for Mars sample return. I don't know if you saw on that slide that Lynn was showing where it said paleontologist and also fan of field trips, because that's how I think I really got interested in geology and got started with my career was, I'm from Oregon originally, so I really enjoy the outdoors and I took a few geology classes and got to go on some field trips and just had a blast and tried to figure out if that was a career path that I could maybe make work. And so I'm hoping today a little bit of what we can do is kind of a virtual field trip of Mars, because that's really what the Mars rover has been doing for the last several years on the surface. So here's a picture of Mars today. We've learned a lot about Mars in the last several decades, but even just looking at something like a picture such as this, you can see a few interesting features maybe jump out to you right away. One of those is the big scar kind of going across the planet's surface. This is Valles Marineris. Essentially, Mars's Grand Canyon, you can kind of think of it as one of the main kind of geologic features just globally present. You can also see a few volcanoes, dormant volcanoes sprinkled on the side here as well. And so, when scientists were interested in Mars early on, it was a lot about, well, where should we try and land, our first spacecraft? And that's always a question that comes up when you're thinking about Mars exploration. So we'll dive into that a little bit, and I'll have a few kind of multiple choice questions for y'all to chime in on the chat and see what y'all think. So here's just kind of a global map of Mars. You can see again Valles Marineris cutting through pretty clearly, and those three volcanoes I just pointed out before. And to the northwest of those is Olympus Mons. That's the largest volcano in the solar system. And so you can see, just several geologic features that jump out to you automatically, such as those, and then this big, huge blue basin down here on the bottom right. That's Hellas Basin, where basically a large impact um, created this feature on Mars early in its history. And so what we're looking at here is basically just a topographic map, right? The red and brown and white areas are higher in elevation compared to the blue areas. So actually, Hellas Basin is one of the deepest places on Mars's surface. And so, when scientists are looking at a map like this, obviously one of the main, kind of first questions that comes out is like, well, where should we try and land? So I'm curious if you had a choice between these different options, where might you want to land your first rover? Obviously, these are all three kind of different, right? We're looking at this more volcanic region over here on the left of the screen, Hellas Basin, which I just mentioned down here. Uh, we have the northern plains up near the North Pole, where B is, and C kind of somewhere right in the middle. So let me see if I can see the chat. Yeah, I see it popping up here. Okay, I see a few C's already. Big fans of C. Any other thoughts? Yeah, A. Okay. Lynn likes A. And I'll tell you what, a lot of geologists, that's really where, their mind first goes to is let's go look at some volcanic rocks that can get a lot of interesting details about that. Uh, I like that answer, Sam. Something about the pit is calling to me. It's always fascinating, isn't it? Thinking about, well, what's down there? Um, and yeah, I mean, this is, really how a lot of scientists think is trying to figure some of that out. Yeah, and then Nate kind of took the all-encompassing approach and said, "Well, they're really all kind of interesting." And then Wendy says, "I feel like C lets you rove more in the
I was
rover."
to say.
So yeah, I mean, these are all good answers. Obviously, you can probably make a case, really for any of these sites. But if I just click through here to the next slide, we can see some of the landers and rovers that we have on Mars surface today, as well as a few other future proposed missions. And one thing that might jump out to you is, well, okay, where are the actual rovers? Since that's what I asked you to land. And the main rovers here from NASA are Pathfinder, Opportunity, Curiosity, and Spirit. And then this other one over here is the one we'll be focusing more on today, which is the Mars 2020 Perseverance rover. And so it might jump out to you then a little bit that like, well, they're all kind of seem to be within the same latitude and longitude, and that's really true. So what this kind of tells us is that landing in the poles is hard. Near more closer or nearer to the equator is typically a better bet just because of engineering constraints. And so, we can get into why that is, but essentially if the engineers tell you, hey, we've got a lot better chance of landing somewhere in the middle rather than near the poles. It just increases the likelihood that the rover will safely get to the surface. And then you can do all the fun science, explore the volcanics, explore the rove around the plains here and things like that. And so, yeah, I mean, all these answers right. We have landed in the poles. It's just not rovers, and it's typically more difficult. But who knows? Maybe we'll get a rover in the poles in the future and maybe even over to these volcanic regions that we haven't yet really explored with the landed spacecraft. And so I guess I'll give it to A and C here just because they're kind of the safer options. But really for the rest of the talk, I want to focus in a little bit on the Mars 2020 Perseverance rover and its landing site, and really what we've been exploring there over the last several years, because those are the samples that have been collected and will ultimately come back to Earth as part of Mars sample return. So what are some of the challenges that we're going to face for Mars sample return? Well, the main one that I'm going to focus on today is still ongoing, and that's collecting samples with the Perseverance rover inside of Jezero crater, which we'll dive more into here. Once the samples have been collected, then we need a spacecraft to get down and retrieve those samples. So it's going to have to go through the same entry, descent, and landing protocols that previous spacecraft have had to go through. Ultimately, we'll need to get those samples back off the surface of Mars. So that's where the Mars ascent vehicle comes into play. And ultimately, we'll need to rendezvous with orbiters and come back to Earth for study by scientists here. And so a lot of this is still being decided, and particularly the architecture or the exact types of spacecraft that are going to do this. But we'll sketch out some broad ideas of what that's going to look like. And we'll focus in firstly on what's going on right now with the rover. What have we been studying? What have we been exploring? And what types of samples might we be bringing back to Earth to study? And if I miss your comments in the chat, I apologies. I kind of have to keep minimizing it and opening it, but I'll kind of keep checking back there to make sure I'm not missing anything. Um, is there a question? Oh, no, maybe just a hot mic.
If
Okay.
there are any left questions, and just
Lynn, your audio is not working.
Okay. Is it Lynn trying to throw a
Yeah.
comment in?
Yeah, Lynn, can you write it in the chat?
Yeah, I'll read out chats if you want
Yeah,
to.
that'd be great. Yeah, thanks. Um, any unanswered questions will be and answered at the end. Yeah, absolutely. I'll
Yeah,
try and leave some time for questions too, for sure. So hold on to them if you got them.
yeah. We'll wait till you're at a break point.
Unless you just absolutely gotta ask it. I totally understand. I've been there. Okay, so now we're looking in on that square I highlighted before where Mars 2020 landed. This is Jezero Crater, and what you might notice from our previous looks at the map is that it's kind of right on the border there of the highlands on the left side of this image and more lower lying areas on the right, and absolutely pockmarked with craters, right? It almost looks more like the moon than it really does Earth. So you might be thinking, well, why did we choose to go to Jezero Crater specifically? Why not some of these other areas? And the fact that it's on that edge of high and low areas uh, lends to the possibility of water because water tends to flow to the lowest lying area. And so the thinking is that Jezero Crater once was actually filled as a lake. And we have evidence for that in these channels that go along the side. So obviously this is an artist's reconstruction of Jezero Crater in the past, but this could potentially be something that it looked like, which if you go to an area like this on Earth, is certainly a habitable environment and a place where life can really perhaps get started and even thrive. And so this was a really interesting locality when scientists and engineers were looking for landing sites on Mars. And so it doesn't necessarily look like this today, but we do have evidence for water there in the past. I mentioned these little channels on the side, but also if you just look at it today, you can see this really neat feature that's present in Jezero Crater, and that's this delta deposit. And so we see similar things on Earth. So you can think of like the Mississippi River flowing into the Atlantic. It's going to deposit similar types of features or landscapes that ultimately got preserved on Mars. So this is what we would call like a river or lake delta, where we have basically sediments flowing in those rivers. That's rocks and mud and dust and sand, basically all kind of flowing and filtering out into the lake bottom. And so this was really good evidence that the sites we'd be exploring had interacted with water on the surface of Mars in its past. Okay, so our rover Perseverance, or Percy as we like to call her, uh, roving down here, landed in the southeast corner of the delta and in on the crater floor, and started taking images and started roving around and collecting some samples. This was back in 2021. And so we'll take a close look here at this area highlighted in the yellow box, which is where we got some of our first really detailed images from the crater surface. And if you pay close attention, there's this little knobby feature right here that I'll show you in the next image. And it's just really cool to see going from orbital images to seeing it on the ground and seeing how those things compare. Really kind of cool. So here's that feature again. And it just looked like a little mound from orbit. But once we got down on the surface, we really see different types of rocks that are deposited in Jezero crater, and this is a really good example. So we call this Kodiak. It's basically a remnant of that delta I was just discussing. And if you look really closely, we have these kind of more magnified images down below. We can actually see different layering within these rocks. And that can be really informative for understanding past environment, past water activity and water flow in the lake or in the delta. And so what we see here are basically different layers that are tilted in different orientations. Don't worry about the names so much here. Trust me, there's no quiz on on geology terms at the end of this, I promise. But essentially, these are indicative of deltas and their formation in water-rich environments, like I was just discussing. So this was really neat to see in the really early days of the mission, and told us that we were in the right area, we were looking at the right things, and what we saw from orbit was now shown as truth on the ground, which was really cool to see. And we see similar things on Earth. So obviously we've got the plants and the sky in the background. So hopefully that gives that away. But we do see similar processes on Earth. So that's how we know how these things were formed. And you can see here the different cross layering in a very similar pattern, kind of highlighted in these with these arrows here. And what those are telling you is essentially different regimes or time periods of fluid flow and sediment getting deposited. You can tell you actually something about the direction in which the water was flowing at the time, or in case on Earth and on Mars, you can also do this with wind too. So what we call aeolian deposits or wind-driven deposits do it. They form a similar thing. So distinguishing between those two can be important, but regardless, you get these different directional uh, kind of deposits both on Earth and on Mars, and we can use those to kind of compare and contrast and study, what that's telling us about the past environment. Okay, so here's kind of an oblique view, same view of that delta. We've got Percy down here in the bottom left. And okay, so and you can see Kodiak there too, that little mound or butte right there. And so now we're sitting here on the crater floor. And we're all looking around, and there's so many cool things to go see and study, but we've got a mission to do. So we got to think about, well, what's our best kind of plan of action? What's going to give us the most return here, or the most bang for our buck, really? Um, so I've laid out a few different paths here, and I'm curious what you all think if you had to decide which one you might choose. So there's our four different options again. I just left it as A, B, C, and D, but I'm curious what you might choose, and you can explain why too if you want. I think they all have some merit. Okay, got it here. I see C, D. Any others?
We got a C and an A and another C. Oh yeah.
Awesome.
D.
C looks tricky with the
Yeah.
lead. Yeah, that's thinking smartly right there.
Then made noted that you could image the crater.
Oh yeah, absolutely. Because this, oh, sorry. I went too far. I gave it away. But there is no real right answer, right? I mean, these are just the kind of decisions we had to think about and play with. So, yeah, I mean, we can kind of go through each of them, right? You can imagine A looking like a relatively straightforward traverse, right? Not having to interact with too much, pretty straightforward, see some things along the way, keep it safe. Uh, Nate says relatively scientific, little scientific value, and I think that's actually a really important observation, right? We probably could have driven up the A route, but I think we may have been missing out on some of the features that we wanted to explore in Jezero Crater. Like I was just mentioning the delta and things like that, obviously, are things of interest. So maybe we'd want to go explore those. Like the sea path here, right? We're driving up the delta, driving by this really big crater, which yeah, maybe is a safety concern, a bit of an obstacle to get around. It's pretty big though, so I like to think we could drive around it. Um, and I think if you would have asked me day one after we landed, I maybe would have picked D here, just because, you can imagine roving around the front of the delta and really getting a good picture of what the rocks look like all throughout that traverse, and then come around and cruise up through the delta too over time and really capture a lot. I'm trying to see, did anyone say B? Uh, B similar to A. I see one, yeah, there was one mention of B. And I think B is really interesting because if you would ask a lot of folks that are working on the rover, involved with its safety and maintenance and want to make sure that it's safe and efficient, they would love B. B would be a great choice because time is kind of the essence, right? And B really is a straight shot. I mean, no distractions. You can think of it that way and just kind of using time to your advantage, getting through as much as you can in as little amount of time. Whereas the other side of that coin, right, might be D is taking way, way too long. We don't have that much time just to kind of rove wherever we want. And, it'd be one thing if we were a geologist out there, we could just take our time, go camping, do a little field trip, right? And explore all along there. But time is important here. It is an important factor. And so, yeah, something in the middle like C seems like a pretty reasonable compromise, although, you're definitely introducing some more complexity and some more challenges with the whole roving aspect of it. So, again, no real right answer, but I probably could have given you a little bit more information here. So, right here, we're not just necessarily looking at different elevation, but the colors here are actually telling us something about the rock type as well. And so you can imagine then if you had known that 5 minutes ago before I asked you, maybe you would have said, "Oh, okay, I'd like to capture some of these different colors." And that would be really true because as geologists, we're always interested in getting a very diverse sample set. And so I think I tried my best to overlay here what the actual traverse of the rover has been so far. So yeah, um, kind of in between what we were looking at, but I think I'd have to give the edge to C if I had to pick a winner from the last one. Although there are no real winners because we'd want to go all those routes if we could. Um, so yeah, and then the rover's now up beyond the crater rim here and is exploring outside of the crater rim and still collecting the last few samples. So now we'll just take a quick kind of tour through some of the different rock types we've seen. So these are some of those layered sedimentary rocks, right, that we looked at before with Kodiak and that kind of knob of delta deposits. So we saw a lot of this kind of layered material as we were driving through. And again, that's pretty good evidence for uh, water lane deposits or rocks that have interacted with water at some point in their history, and that can be really useful for searching for signs of life. And so, we definitely snagged a couple of samples of those along the way. As we kept going, we started getting some really beautiful landscapes. Here we see some of that difference in elevation, right? We can see some higher topographic areas like these hills, and I probably wouldn't call it quite a mountain, but certainly a raised up hill there. And if you look at in the foreground here, up real close, a lot of similar looking rocks and a lot of dark colored rocks. I think that's how a lot of us just kind of first described them was, uh, wow, there's a lot of dark rocks there, and most of that is volcanic in origin. It's actually basalt. It's things you can go out and see. I grew up in Oregon, so if you drive through the Columbia River Gorge there, you see big basalt flow deposits. And it's the exact same type of rock, and it's all formed from ancient volcanic activity. So this is kind of a typical scene, what you see roving through in the very rusted environment of Mars, right? Um, and so one thing we're always kind of looking out for is, well, what sticks out from the background? What jumps out at us as we're roving? Because again, time is important, so we want to, be conscious and diligent about the decisions we make when we want to go study a particular sample on Mars. Yeah, a couple more vistas here, some landscape images. Sorry, looks like I didn't label the top image here. But looking, I think northward across Jezero Crater there, where we're seeing some more of the fan and perhaps delta deposits here as well. And some of the highlands further in the background there. And then on the bottom, this is Neretva Vallis. This is that big valley that's basically carving into the crater, right? I mentioned those channels that would have been bringing water into Jezero Crater before. This is looking basically back down into one of those valleys, and it and is a place where we spent quite a bit of time exploring, just because we had some good context for what we were looking for there. Yeah, and in that valley, so this is still in Neretva Vallis, we crossed over this mound in the middle, and again, you see a lot of typical dark rocks, but something else probably jumps out at you there, right? And it certainly did as we were roving past it. Saw this big white boulder, and it really caught a lot of people's eye just because it stands out a lot from the background. Obviously, probably has a different origin from the other rocks around it. We even see some kind of like purplish rocks up here, which is pretty neat too. All of these things were obviously really captivating as the rover was going through Neretva Vallis. And let's see, I think I have one more here from a similar area. Yeah, look at that one. This is what a lot of folks termed the zebra rock, right? Makes a lot of sense. It looks just like that. And so these lighter toned rocks with different amounts of black minerals in there, obviously really, really interesting. Unfortunately, we didn't actually collect a sample of one of these rocks, and there's actually good reason for that. So a lot of the samples we look to collect, we want to find them in place. We want to find them where they're exposed together with a big block of that same rock type. And so essentially, these white rocks, while they're really interesting, and we did stop to take some really good images, um, we don't necessarily know exactly where they came from. And so not having that context, not having that understanding of their source, or what we call their provenance, that challenges the reasoning for collecting them and basically using a sample tube to store those rocks, because yeah, we might be able to study them back here on Earth, but we won't necessarily know where they came from, or how they formed, or what other processes were happening when these things were were turning into rock in the first place, right? And so that context is always really, really important for a geologist, uh, even if it's a robotic geologist. But nonetheless, these are the types of things that, really stand out from the background and really capture our interest and make us think and ponder, should we go spend some time there? Should we use a sample tube? Or should we, kind of hold off and maybe hope we see it in place somewhere in the future. Really tough decisions that have to be made in a short amount of time too. So you can imagine these are really things that the scientists and engineers really wrestle with and grapple with when they're thinking about sampling on Mars. Okay, I've got another one for you here. So this is a kind of typical almost landscape of Jezero crater in some regards. But what we see here is definitely some different types of rocks. And so you've probably noticed that we're zooming more and more in as we go on. And so I thought this was a good opportunity to say, okay, so you've got this landscape in front of you, and you've got to pick one. You've got to just pick one that you can go to and try to collect a sample. Which one you going with? Let's see it in the chat. So we've got A, which is this lighter tone material over here on the left side. B, the green dot is up here with these lighter tone materials, a bit flatter. C, the dark toned rock, and it can be really any one of these dark toned rocks. Doesn't necessarily have to be that one. Or I put D down here too. This is essentially the sand or the regolith, where we have some really nice exposures of that here too. Curious what you guys think. Oh, I like that, Lynn. Yeah, try to get a 2 for 1, huh? A or C seems interesting. Possibly C, yeah. See a lot of votes for C. And I'm guessing the thinking there is, well, most of it's light tone. Maybe I want to get some of the dark stuff just because, it's looking different from the background. That's what we were just talking about. Yeah, and I think, it maybe comes down to what can we get to, what can we access, and Seth, never mind. A, C looks like you get a wide variety. Yeah, I mean, I really love some of the observations y'all are making about the different types and different tones of rocks and different textures. These are all real kind of key words, really, that we pick up on as well, and try to focus in on and really give ourselves the best chance of success. Ultimately, again, if time's of the essence, you want to make sure if you're going to go there, spend the time, make the measurements, collect the sample, you want to succeed. And so, I think part of that, especially with the rover, one thing it really benefits from is flatter surfaces. So some of these textures, while really interesting, even this one up here, it's almost like spider-like or web-like now that I look at it. Really, really interesting, but might be tough for the rover to either analyze and study with its instruments on board. I didn't go a lot into the instruments on board. It's kind of a separate talk. You can certainly go and look up what different instruments. There are a lot of, you know, uh, types of different types of ways of measuring the chemistry of the rocks is one thing we're really interested in with some of those scientific instruments. But yeah, I mean the surface really matters, and so just looking at this, if we could get there, I think maybe B might be the best option just because it's really flat and we might give ourselves some more chance of success there. But on this one, it's kind of like one of those freebies on a multiple choice. It's really all the above. So I don't think you could go wrong there. And I'll actually show you a good example of that here in a few. So once we decide on a spot, I mentioned that, flat is typically better. This is a good example of that. This is what we would call an abrasion patch. So it's kind of the first step we take before we collect a sample is we abrade it, we grind it down essentially. You can imagine just taking a, a chisel or something like that with some sandpaper and rubbing it in a circle. It's basically what it does. We have an abrasion bit on the drill, and we put that on. We grind a few millimeters maybe down, and what that does is it really gets rid of a lot of the surface weathering, essentially how, the sun's been beaten down on it for who knows how long. And so getting below that upper surface is really beneficial for a lot of the types of analyses we like to do. So we might make an abrasion bit like this, make some measurements on it just to get an idea of what types of minerals are there, what type of rock is it, to the best of our ability. And we'll try to avoid the cracks and things like that as best we can. And this was a really nice one. This one actually looks pretty uniform. We don't always get that lucky because you just don't know what's lingering right beneath the surface. But this is kind of our step one in our sample collection. And if we like what we're seeing from the instruments and we're moving on to, the next step, next phase is, okay, we want to collect a sample. Well, now we got to go find a new flat surface. And if we're able to do that, then we can take out the drill, start drilling ourselves a core. You can actually see there on the right of this image too, our previous uh, abrasion right there, abrasion patch. And so we just went, maybe 6 inches or so away from that and took our sample here. And so that's essentially we're taking different images here, stitching them together to give ourselves an idea of what the drilling process looks like. You can see it creates a whole a whole mound of sediment and dust that collects around it. But ultimately, the goal is to bring out a solid rock sample that we can then collect and stash and hopefully return to Earth in the future here. And so that this gives you a sense of what that really looks like. And just as I mentioned a few slides ago, we have the light rock, we have the dark rock. They're right next to each other. So I saw a few folks say, gosh, if I can get a 2-for-1, that's even better. And we really think along those same lines, as if we can get the rover close enough and we can make 2 abrasions here. We got one up top on the dark rock, one down below on the light rock. And this was collected after we took a sample on the lighter tone rock down here. You can see the uh, the pit there where we essentially took our drill core. And if we're successful, which we aren't 100% successful, but we mostly get them intact, you can get something like this that we can take an image of once we've got the drill core in the bit. We can basically take it, preserve it, keep it in its sample tube, store it, and hopefully pass it on to be returned to Earth in the future. So that's generally the kind of process. That's generally what it looks like. And this imaging is really important because it tells us that, okay, we actually got in our sample what we saw in the rock, in the outcrop, right? And so that's really important just to confirm that. I think someone asked about this earlier. Did we ever store the samples on the surface so we can collect them in the future? And before the rover drove up out of the crater, that it did do that. So it deposited, I think, 10 of the samples on the crater floor. And those were all collected in essentially in duplicates. And so we had doubles, right? If you ever collected cards or anything like that, you always had doubles. You said, okay, I'm gonna keep my best one and trade my trade my other card for a new one, right? It's that kind of idea, right? We took two, we stored one on the crater floor, and we kept the other one on the rover, and we kept collecting as we went. And so the hope is that if we are able to bring these samples back, we'll be able to get the ones that are on the rover now. There's going to be more of them. They're going to be kind of our better samples that we kept on the rover. And so that's the main goal right now, is if we are able to bring the samples back, we want to link up with the rover essentially and hand off those that it has on board. But as a contingency, as a backup plan, we do have these other sample tube duplicates that were sample duplicates that were dropped on the crater floor to hopefully collect in the future. Even if we get the ones on the rover, we can these will be there for a long time. No dust will cover them up where they're at. So hopefully we can even bring these back one day. It'd be really cool. So here's looking inside actually one of these sample tubes with a rock core in it. This is a really cool kind of piece of technology. This is a CT scan actually looking inside of one of the sample tubes. So you can see before you even open it up You can get an idea for what's inside, what it looks like. You can see the rock core in there in the lighter color. And then actually at the top where there's no rock, you can kind of see here on the right here. Uh, Kind of cool. We get another little two for one because we get some Martian atmosphere trapped in there. And so folks that are interested in, the evolution of its atmosphere, what that can tell us about its climate, all those sorts of things, some of those questions will be able to be answered just using the gas that's trapped inside these sample tubes as well. Really kind of a cool tidbit. See, how am I doing on time? I know I'm getting close here. We're on the sample return part, right? So we've got our sample tubes. We're ready to bring them home. What all do we have to do? Well, we got to get down to the surface. I'm showing a video here of when the Perseverance rover landed. We use this sky crane technology. Really, really cool. And we'll probably implement something similar to get the sample retrieval lander on the surface as well. And ultimately, we'll need to land again. We'll need to transfer those sample tubes that we've collected, store them, contain them, and ultimately prepare to bring them back to Earth. And so, a big task of Mars sample return is just getting back down to the surface again. We have to time it right. We have to get the angles and descent and propulsion all right. The sky crane has to work properly. So it's a very involved process, and the engineers are really amazing at what they've been able to accomplish in terms of landing on Mars. They've had some success. I have quite a bit of confidence that we can do it again. So once we make it down, I mentioned the kind of handoff, and it'll probably look something like this. This isn't obviously the exact technology that'll be used, but the idea will be that we need to take the sample tubes that we've collected and safely transfer them onto the sample retrieval lander. We hope to bring back some 30-ish samples, uh, mostly rock cores and some sediment or regolith samples as well. Potentially an atmospheric sample that does not have a rock inside. But ultimately, you'll need to pass off the sample tubes and do that without, obviously damaging them or anything like that. But they'll need to be contained as well for their traverse back to Earth, which is no small feat, as we'll see here in a second. So we've got the sample tubes on the lander. Now we got to get them back. This is probably the biggest hurdle of Mars sample return is the Mars Ascent Vehicle, or the MAV. So this is a rocket that will need to be built to carry the samples off of the Mars surface, and it will be the first rocket ever launched off of another planet. So it's really unprecedented. We've never, done this before, obviously, and it's new technology that will need to be developed to reach that escape velocity here on Mars, which is basically the minimum speed at which you need to get past Mars gravity before it wants to pull you back to the surface. And so to get off the surface, we need a lot of thrust. And for depending on how massive the rocket is, you need more thrust, and more thrust is more expensive. And so all these things are kind of feedback in on each other. And so really the one of the main goals right now with Mars sample return is we need to, kind of decrease the size, decrease the mass, which means we need less thrust to get off the surface, which essentially means we need less money poured into developing this technology. And so it's a lot about, and this is kind of the case for, all of Mars exploration really is, you have to kind of miniaturize things and still have them work. And they have to work the first time and they cannot fail. Because once they fail, you can't just send your technician, your uncle out there to go and fix it up with a wrench and ratchet, right? So it needs to be essentially built perfectly the first time. Now there's some, troubleshooting that we can do here on Earth with the software and things like that, but it really needs to be be done right the first time. And so this is one of the biggest challenges that I think Mars sample return really faces, and I'm sure we'll find a way to overcome it. So this is something that we're really working a lot on right now. Okay, let's assume all that goes well. We've made it to Mars orbit. Well, that rocket that just left Mars is not strong enough to go straight back to Earth. It's going to have to link up with something in Mars orbit and ultimately either dock with it or transfer the samples that it carried onto what we call an Earth return orbiter. So this will have its own propulsion system to bring it back to Earth. And you're thinking, how the heck are we going to meet this tiny rocket with this orbiter in space? That sounds really difficult. Uh, Fortunately, NASA has quite a bit of experience at this. This is a clip of one of the Apollo missions launching back from the moon and rendezvousing with the command module in orbit uh, around the moon and preparing to bring the astronauts back to home. And so obviously they had, humans at the controls. We're doing this all autonomously and all robotically, but the technology is the same. The principles are the same. The physics is the same. Well, I shouldn't say that. I'm not a physics expert. I'm sure there's some major differences, but the principles are the same. Linking up together in space, getting on the right trajectories, docking, and ultimately propelling back to Earth for eventual Earth entry. And again, another similarity about Apollo and what we're doing on Mars is, well, they were bringing back a lot of samples too. And so, this isn't new. This is just a new era of space exploration. And I know there's a lot of excitement about kind of increasing our inventory of return samples from samples from the moon and in the future, hopefully samples from Mars. So keep your fingers crossed. Yeah, the Earth Return Orbiter is going to be quite an impressive spacecraft. It will be more than twice the wingspan or twice the size of previous orbiters around Mars. So again, really unprecedented in its development and its design, and will kind of be the last major step in bringing these samples back to Earth. And so it'll have its own propulsion. It'll be sending the samples back away from Mars, back to Earth. And then the final step, right, is getting back through Earth's atmosphere, which is a challenge in its own right. We have quite a bit of experience with that as well. We've landed other samples from asteroids back on Earth and things like that. But the last major step will be going through the Earth's atmosphere safely and without damaging the samples, without it burning up, and ultimately landing on the surface for us to collect and contain and hopefully start studying. And there's all sorts of really cool stuff we can do with those samples once they're back. I think I'm running up on the hour here, but I am on the last few slides, promise. So what happens once we bring them back? We've got our samples we've collected. There's so many neat things we can do, right? We talked about different sample types that we'll be bringing back, some that were deposited by water and that will tell us about past environments, about past habitability, about the conditions in which life may have been present or may have flourished. But we'll also be getting back like volcanic rocks and things like that, which will be really a first. I mean, all the samples will be a first from another planet. But the volcanic rocks we can use for age dating will really give us some valuable context for when all these things happened on Mars and really give us some kind of brackets on the timing of these processes and when they all took place. So, was it very early in the history when impacts were still, happening on Mars surface and affecting things around? Or was this a much more recent deposit where, we had some water that maybe flowed intermittently only, several millions of years ago? And it's very hard to tease those things apart when we're roving around on the surface. We just don't have the technologies all the time available to us. And that's what we really, really need those, kind of state-of-the-art laboratories on Earth. That's really what will enable a lot of the science to be done is once we get them back in researchers' hands. And finally, with those samples, hopefully we'll be able to start probing the question or continue probing the question of the search for early life on Mars, which really is a highlight of the field of astrobiology. This is, a lot of what my background's in is looking for things like this. This is a good comparison with our other rover. This is Curiosity here, actually, in Gale Crater, where they've had discoveries of organic carbon-based, hydrocarbon-based molecules and chemistry. And these are the types of signatures that could potentially tell us about the possibility of past life on Mars, and certainly something that I and my fellow astrobiologists and other chemists and geologists will really be interested in studying is some of the organic molecules that we hope to be able to find and discover in these rocks, which we've already kind of stumbled on. So there's a hint that they might be there. Lastly, I'll leave you with this one of the most recent samples we've collected, a really peculiar rock on Mars. This is the Chayava Falls sample that we collected, and you can just see it's certainly not something that we typically see on Earth. It's not a common rock type. It's got a lot of interesting features going on with these white bands going through. And then you probably notice some of these kind of circular features that a lot of us have just been calling leopard spots because that's kind of what they look like. You don't know much else about them. So you can go and Google Mars 2020 leopard spots and read all about them. And there's some really interesting possible chemistry that's going on there with iron and phosphate and different elements, as well as these white bands, these sulfate veins that are going through, which can tell us just a ton about the past environment and processes and potential interactions with water that may have been taking place here. So we've got our drill core, and yeah, again, you always want to kind of peek at the bottom of it, and still we see some of those leopard spots present there, which was really, really neat and exciting to see. So those will almost certainly be coming back for us to study, and I know a lot of folks are looking forward to getting their hands on some of those samples and looking at them more closely. Be really exciting. Okay, lastly, I'm just going to leave you with a few resources. There's a lot of stuff out there, but there's a few good websites I think you can jot down and check out if you're really more interested in Mars and in astrobiology and in NASA and the science and engineering and all the things that they're involved in. NASA has a lot of good online resources, and I would also encourage you to, seek out. Local opportunities. There's a lot of folks that are doing work at different universities that you may be near or museums. Always kind of keep an eye out for different activities or opportunities to get involved or even just learn more. I think that's where a lot of it really starts, even for a lot of folks that end up working for NASA. They're just really curious and passionate about Mars or other planets or solar system bodies. And everyone kind of started somewhere. So I know for me that was certainly the case, and I really kind of got interested in Mars first, and then came back to Earth and started studying geology here because obviously that's where we get a lot of our information and our knowledge to go and explore places like this. And so, another thing you can always do is take a geology class. I didn't take one till I think I was maybe halfway through college. I hadn't taken a earth science or geology class, so I certainly encourage you to do that because I know once I got in there, I was just fascinated, and it was really easy to work hard on it because I found it so interesting. Yeah, I think this is a really good resource too here. You can go to astrobiology.nasa.gov. It has kind of the career path suggestions here. So, really outlines, I think, very clearly a good place to start. Just read books, read books, listen to podcasts. I'll show you the YouTube channel here in a second. And if you're headed to college or if you're in college now, you can start thinking about, the different fields. All these fields you see here on this page are, involved in astrobiology, in Mars exploration, in solar system science. And so, not everyone fits into every field, right? You might find something that you gravitate a bit more towards, that you're a bit more interested in. See where that goes, take a few classes, see what you can learn, either online or through, like I said, your local institutions or nearby universities or something like that. I think I had to take classes in all of these subjects at one point, but I really gravitated towards geology and biology. And a huge part of that is chemistry. So really, you start seeing how they all kind of blend together. And then if you want to kind of continue on, there's other opportunities as folks go into grad school and do a master's or a PhD. Something you can start thinking about. I wouldn't worry too much about it now, but just know that there are resources and opportunities out there, and NASA, I think, does a really good job at making those accessible to really everyone, especially if you're in this stage of learning and if you're really interested. So yeah, keep an eye out. And this page is constantly updated and is a really good place if you're interested, just a nice place to get started. And I mentioned the NASA YouTube channel. They have some really cool uh, videos on there. The NASA Astrobiology hosts, I think it's a monthly, maybe. Uh, Episode of Ask an Astrobiologist, where they bring on a different expert. And astrobiology is such a broad field. You get exposed to so many different types of scientists and engineers, all working on all sorts of different things. It's a really great production, and I know there's a lot of other really cool videos on there, some more geared towards Mars or whatever it is you're interested in. So I encourage you to go down that rabbit hole because I think that's where a lot of us originally started. And finally, I think it was mentioned at the beginning that I work with NASA Scope and NASA Science Activation. And so this is another really good resource for opportunities that might be available to you locally. And so I would definitely suggest checking that out, seeing if there's any organizations or any teams, SciAc teams that are around you, and see if there's any opportunities to get involved. And I know, a lot of the folks that I've met that work in this field and work for NASA and work in outreach and in science and space exploration, it's some of the greatest people I've had the pleasure of meeting. So it's a great community, and yeah, I really hope that you guys find this interesting and have an opportunity to interact a little bit more with some of the work that's being done by NASA and folks interested in Mars exploration. So I hope you enjoyed that. I hope I left enough time. It looks like it did go a little bit over. My
Oh,
apologies.
you're sort of over, so I'm not sure we have enough time to do any questions
No, no
because we
worries at all.
normally
I
end at about
apologize for running over.
yeah, we normally end about 10 minutes to the hour. But it was so
Okay.
interesting that I didn't want to cut you off.
Yeah.
No, I just totally lost track at the end there. My apologies. But thank you guys so much for your attention and the opportunity to speak here. I really appreciated it. I had a blast running through those with you.
Well,
And
I had to stay tuned because
This is so cool.
I had to learn how you were going to get this stuff back down to earth.
Yeah, exactly. Exactly.
It's like a story that we needed to know the ending.
yeah, well,
Okay.
We
it's not going to
can,
be easy.
well, I think this group probably knows. Maybe we'll just we don't have to explain. I think they know why we're doing this. So maybe we'll just quickly put the
Yeah,
question.
unfortunately, I don't think we have any time for Dr. Osterhout to answer the questions in the chat, but we saved the chat, so maybe we can send them to you and you can let
Yeah,
us know the
absolutely. And
answers.
hopefully I answered enough of your questions uh, going through.
Yeah.
Okay,
And
so
that,
here's our questions for the intern community that has stayed with us.
Yes.
You could just put your answers in the chat, even if it's NA because you don't know what to answer for not applicable.
Yeah, I'm curious to hear see what folks
Yeah.
say.
So this is what we ask every time. It's part of our evaluation process.
Awesome.
Is my screen sharing?
Hmm.
Yes,
Oh,
it's
Oh,
working.
good.
And the questions in the chat as well.
So for yes,
maybe
for
I have to.
those of you students that are still here, please answer.
And Jeff, if you like scroll a little up into the chat, if there's any questions that are there that you want to respond to, you can even do that. All right, should we go to the next? Oh, good. Thank you.
I think people are still typing.
Yeah. Okay.
We have astrobio and rovers are fascinating. Samples of rocks are taken by rovers from the valleys and craters of Mars. Learned about the different aspects of collecting data on Mars environment and a bunch of examples. Sorry, my cat.
Yeah, and I saw Nate mentioning the Earth return orbiter and thinking about how it's going to get back and trying to make that as efficient as possible. I'm not sure about ion thruster. I'd have to double check ion thrusters. And again, I mentioned this at the beginning, but some of this is still kind of being decided and figured out and researched. And so we're trying to figure out the most efficient and effective ways to do this. Uh, NASA's hard at work on troubleshooting a lot of the challenges that we mentioned, and I think trimming down the weight of particularly the Mars Ascent Vehicle, the MAV, is going to be really important, um, and because getting off the surface again is going to be one of our biggest challenges.
The next question is on the screen and in the chat.
Mhm.
I'm just going through and loving these answers because this is awesome. It's really great to be able to kind of speak with the next generation, really, y'all are the folks that are going to be carrying the torch and kind of like I mentioned, we all started somewhere and we were all students at one point who, I'm sure the case was the same for me. I saw an interesting talk or got captivated one day and started exploring a little bit further and somehow convinced myself that I could make it a career. But I will say, it once you find something you're interested in, it makes it a lot easier to kind of commit and really, dedicate yourself and work hard on something because it's something that you're naturally interested in. And I think that, fellow scientists can resonate with that because a lot of times we're just kids. We just stay curious.
Right? We got yes, sure. Question orange. Question three. If you don't have a good answer, just put NA or whatever. Or not applicable because you don't know what to say. All right, we got some NAs. Let's put up the last question since we're so late now. Plus, I got a basketball game starting in 15 minutes. Go Warriors!
Yeah, do differently next time. I think I either gotta speak faster or cut a few things out. It's hard though. I have a hard time deciding what to leave out.
I didn't even notice all that time passed, so it worked.
Well, that's good. That's good to hear.
Amazing how much Mars looks like the southwest of the US, doesn't it?
It really does. They actually do a lot of training out there just because it's such a similar type of environment. And yeah, I mean, there's certain pictures where like if you change the sky to red, I'd have a really hard time telling you if it was on Earth or on Mars. So yeah, definitely.
Yeah, those recent photographs, which I had, images which I had not seen, were just spectacular.
Yeah.
Really.
Yeah, they're really fascinating. Absolutely. Yeah, and
And then so,
most of those, I think all of them, you can readily get online, get access to. They have, these are publicly released, so you can just go on NASA's website, type in NASA Mars images, and really kind of start pouring through all sorts of them. But then you run into problems like me. You start looking at them all, and you burn 4 hours.
Well, that was just wonderful. So thank you so much, Dr. Osterhout, and we we will hopefully you'll give us permission to post your recording on our N3 intern channel, and we have been recording this, so
Yeah.
And please share your PowerPoint with us so that we can
yeah.
Okay.
um,
Yeah, I can do that.
put it within our bookends and then we save that so we can have access to it in the future.
Yeah, sure thing. Well, thank you
Uh,
guys so much. I really appreciate the opportunity to speak with you. I apologize again for running a little long. Thank you all for hanging in there and sticking with us till the end. Um, it was a really fun to talk about it with you guys and run through some of those hypotheticals and think about that. So I really enjoyed it and hope you learned a few things.
well, thank you so much. Okay, everybody, we're
Enjoy
not
the
sure if
best.
we're going to
Enjoy the
have
game.
a meeting in May, but we'll be definitely back with another science talk in June for the larger N3 intern community. So but we may still have one in May. I haven't quite yet figured out if we can sneak another one in. Okay, thanks everybody. We'll
Awesome.
Bye,
Thanks
see you
everyone.
again.
soon. Okay,
Bye.
Thank
bye.
you.
Bye.